Greetings to all participants. I'm very happy to participate in the MARTECH 2022 conference, and special thanks to the conference organizers for all of their efforts. Firstly, let me present myself shortly to you. My name is Manolis Annetis. I'm a naval architect and marine engineer, graduated from the National Technical University of Athens, and I'm currently working as a research engineer at the NTUA in the research group of Professor Ventikos, the Maritime Risk Group, focusing mainly on environmental engineering, human factors, risk analysis, and maritime safety. My presentation is about the conference paper entitled Operational and Economic Assessment of the Flapping Foil Thruster Propulsion Innovation Performance. My co-authors are Professor Nikolaos P, Professor Kostas Belibassakis, as well as my colleagues Panagiotis Sotiralis Evangelos Filippas and Eirini Stamatopoulou, all from National Technical University of Athens. In this presentation, I will firstly introduce you to the context of our study, which is conducted within the SeaTIC project, for which I will also say a few words. Afterwards, I will present to you the background of our study, which refers both to the flapping foil thruster systems and life cycle approaches. Then I will introduce you to the methodology of appreciating the combined performance of the foil and the ship's engine, while I will also present the developed LCCA framework, which is utilized to provide the economic performance of the system. Finally, the results, both operational and economic, will be laid down, while conclusion points and our future work on this study will conclude the presentation. During the past few years, but also in the decades to come, all industry sectors are trying to adapt to a new circular and sustainable economy mode in order to limit the socio-economic consequences of climate change. Thus, decarbonization is crucial for all industries. In the context of maritime industry, many attempts are made to provide technologies which will reduce emissions and fulfill ambitious targets set by the International Maritime Organization towards decarbonization. To deal with this challenge, CTIC Project is developing two innovations, a dual fuel engine of high efficiency and a flapping foil thruster innovation, which will be the case in this paper. The paper examines both performance enhancement from the operation of the foil thruster and the economic aspects through a life cycle cost analysis framework. SeaTech Project has been funded under the Horizon 2020 program and aims at developing these two symbiotic innovations, a dual-fuel high-efficiency marine engine and the propulsion innovation, namely the flapping foil thruster innovation, or also referred to as dynamic wing. SeaTech Project is expected to result in a 30% reduction in fuel consumption for short sea shipping cases. It has started in 2020 and will conclude in May 2023. Wärtsilä is the coordinator of the project, while both academia and industry partners are completing the consortium. In respect to the foil thruster innovation, the concept is that it utilizes energy from wave-induced motions, such as pitch, and converts it to propulsive power. This is achieved through thrust production and reduction of the ship wear resistance. It is considered to be located at the bow, where it is more efficient, in a depth around the ship's baseline and slightly in front of the hull. In extremely calm seas, the foil may increase resistance and therefore power demand, while at rough seas, it is not safe to operate due to strength restrictions. Thus, it operates only within a range of sea states. The overall enhancement is shown to be significant by previous studies, and there is a prospect for higher levels of performance enhancement. On the other hand, life cycle approaches are very important as they provide a significant insight even from the early stages of design. They include all necessary life cycle phases, which can be adapted in respect to the system under consideration. Most importantly, though, they allow shifting between different configurations and alternatives in order to choose the most cost-effective solution. As life cycle approaches, life cycle assessment is used for environmental assessment, while life cycle cost analysis is used for the economic assessment, which is the case in the present paper. In terms of methodology, for appreciating the combined performance of the foil thruster, in combination of course with the standard marine propulsion system, the presented data were utilized. In more detail, after assuming a reference point in the North Sea, which is characterized by dense marine traffic, wave data were generated for a large population from the bivariate probability density function model. These data are systematically used in conjunction with propeller performance data, ship responses, as well as wave added resistance from systematic series, and finally, flapping foil thruster performance data, in order to calculate with all of these the ship engine performance in head waves with and without the flapping foil thruster for the whole population of waypoints. The methodological approach for the introduced LCCA framework includes the steps that are shown here. First comes the problem definition, which is defining all costs for the economic evaluation of the foil thruster installation. Then, the breakdown analysis identifies all cost elements. The first distinction, of course, of cost elements are the 4 life cycle phases that I will show you in the next slide. Then comes the analysis in smaller costs, such as individual cost of parts and components in construction phase or consumptions in the operation phase. Cost modeling is the way of approximating the cost. 3 models are mostly used: the analogy, parametric, and engineering. The analogy model utilizes data from similar systems. Parametric model scales up and down the respective costs in order to approximate the cost of interest, and the engineering model is a detailed and reliable way of mathematically calculating the costs. Afterwards, all available data are collected and the costs are calculated in their present value in order to finally evaluate an investment regarding the foil thruster. The feedback loop that is illustrated here is very important, as it stands for the iterative process of the LCCA framework. According to this process, all steps should be repeated and improved due to the unavailability of data in the early stages of the product development. The gradual availability will allow more realistic and precise results. The 4 phases of the LCCA framework are described and illustrated here: construction, including retrofitting costs; operation, which mainly refers to fuel consumption; maintenance, either on board or dry dock; and disposal. The figure shows the breakdown of the most cost elements that are already identified. Here are the combined performance results generated from the data presented earlier. For the service speed of 15.2 knots for the given location in the North Sea, the expected improvement by the operation of the foil is illustrated in this figure. The black solid line indicates the increase of calculated power in kilowatts due to waves, and the red solid line the expected improvement due to the operation of the foil thruster in waves. The red dashed line indicates the mean expected enhancement compared with the black dashed line. As a first estimation at the ship's service speed, the overall expected performance enhancement ranges from 2 to 7%. In addition, this figure shows us the limits of the operation of the foil. On the one hand, the sea states with low significant wave heights at approximately 2 meters, the foil may contribute to increased power demands, while on the other hand, the sea state with significant wave height of 5 meters is considered as an upper limit from the point of view of strength and safety requirements. The previous calculations are exploited to show the corresponding operation points of the engine propeller diagram. The operation points above the calm sea condition, the black dashed line, correspond to the increase of power due to the added wave resistance effect. On the other hand, the operation points of the propeller curve below the calm condition indicate the improvement of performance due to the operation of the dynamic flapping foil thruster. These operation points would remain above the line of calm condition along the propeller curve if the dynamic thruster wasn't operational. The sea state with significant wave height of 5 meters is considered as an upper limit from the point of view of strength and safety as stated earlier, and thus results above that limit are excluded from the calculations that are considering the effect of the foil. Some indicative results for the construction, maintenance, and disposal life cycle phases are shown in this slide. The breakdown structure of the system in a first high-level attempt was developed based on existing systems on board, such as airframes, fin stabilizers, hydraulic systems, cranes, and others. The concept for the system structure is illustrated here, while the high-level component analysis is presented in this table, along with the costs and benefits from the 3 phases. Cost modeling follows the analogy and parametric models, as the engineering model is still under process in the context of SeaTIC Project. Data were made available through manufacturers, product guides, and industry experts to approximate the costs. For the operation phase, in order to show the economic performance of the foil thruster, a comparative study between engine performance without the foil thruster and with the foil thruster is underway in the context of SeaTIC Project. As shown earlier, operation costs include mainly fuel and lubrication oil consumption. These are calculated through the presented equations. Power demand in kilowatts is extracted from the combined performance results that were presented earlier. The specific fuel and oil consumptions are given from the engine manufacturer as a function of the engine load for either ULSD or LNG as marine fuels. For the operation time, 8,700 hours are assumed yearly, from which the 7,400 are in seagoing operation. From these hours, based on the whole population of wave condition presented earlier, the foil will be operational for approximately 28% of seagoing time, namely 2,080 hours. Thus, the respective power demand, either with or without the foil, is inserted into the calculations in order to estimate the fuel and oil consumptions. The prices for fuels and oil are then inserted into the calculations to provide the respective costs. Calculations are in progress within SeaTech Project, but are not yet mature enough to provide with a safe conclusion for the range of the expected benefit from the foil operation. Experimental studies through sea trials of large-scale model in the next months will provide us with more safe and reliable data. In conclusion, taking into account that the present results of the combined performance contain an error associated with the cumulative inaccuracy of the application of systematic series data, they constitute first indications and trends of the performance of the foil thruster in combination with the ship engine propulsion system. It is shown that the use of flapping foils could augment the overall propulsive efficiency of ships and reduce engine load by extracting energy from waves, as well as simultaneously damping the oscillatory ship motions. This effect is more significant in moderate to high sea conditions, while in calm or extreme weather conditions, a retraction mechanism for the dynamic foil system is required to avoid increased power demands or damage respectively. The concept shows significant prospect and is likely to be applicable to a wide range of ship types. On the other hand, the developed LCCA framework is a useful tool for the continuous economic evaluation of the foil thruster innovation by providing useful insight for decision making during its design and development. The first LCCA results, despite their low maturity, are encouraging since they show a significant economic benefit from the operation of the foil, which counterbalances the construction and maintenance costs. Future work is necessary to thoroughly define the economic impacts and to deal with the uncertainty and risks that have impact on the flapping foil thruster's life cycle cost performance. This will include detailed construction, maintenance, and end-of-life phases when more information about the system structure will be available. A more detailed voyage scenario considering multiple map points with the respective sea state variation, uncertainty analysis for the material and fuel prices, and capital budgeting methods such as net present value to determine the long-term economics and financial profitability of the investment. Thank you very much for your attention. I'm happy to answer any questions, and my mail is also available for anyone who wishes to contact me.